Welcome to the Explainer. Today, we are opening up the essential toolkit for understanding how electronics actually work. We're going to demystify the fundamental laws that are really the bedrock of every single circuit you have ever used.
All right, let's kick things off with a super common problem. You've got this tiny, delicate little LED, and then you have this big, powerful 9-volt battery. Now, if you just hook them up directly, well, that little light is going to flash brilliantly for about half a second and then pop. It's toast. So the real question is, how do you tame that power so they can play nice together?
You know, to solve this puzzle and to understand pretty much any circuit, we first need to get a handle on the three basic ingredients of electricity. Think of them as these invisible forces that are all around us, but once you know the rules, you can totally control them.
At its most basic level, electricity is just the movement of electrons. I mean, these tiny little particles create a charge, and if we can get that charge flowing in a predictable way, we can make it do all sorts of useful work, like, lighting up your house, playing your music, or powering the very screen you're looking at right now.
Okay, so since we can't actually see electrons flowing, these concepts can feel a little out there. So to make them super intuitive and easy to grasp, we're going to use a really simple but honestly a brilliant analogy, a water tank system. So first up, we have voltage. The easiest way to think about voltage is as water pressure. It's all that potential energy just stored up and ready to burst out. The more water you've got piled up in that tank, the more pressure you're going to have pushing out of the hose. In an electrical circuit, this pressure is the difference in charge between 2 points, and it's what gives those electrons the push they need to get moving.
Okay, so if voltage is the pressure, then what's current? Well, current is the actual flow. It's how much water is actually moving through that hose in a given amount of time. We measure this flow of electrical charge in amperes, or just amps for short. It makes sense, right? More pressure, more voltage is going to give you more flow, which means more current. And the last piece of our puzzle is resistance. In our water analogy, resistance is simply the width of the hose. A big, wide-open fire hose has very low resistance, so tons of water can flow through easily. But a tiny, narrow coffee straw, that's got really high resistance. It's going to fight that flow of water. Every single component in a circuit has some amount of resistance, and we measure that in a unit called ohms.
So let's just put it all together right here. You've got an amount of water, which is your charge. The water pressure, or voltage, is what pushes a certain flow or current through a hose whose width or resistance can make it easier or harder for it to get through. See? These three things aren't separate ideas. They are completely and fundamentally linked. Now, let's grab our first master tool from the toolkit and see how this all leads back to solving our little LED problem. Because, understanding the relationship is one thing, but being able to calculate it, that's where the real magic happens.
So back in the 1800s, a Bavarian scientist named George Ohm realized that this connection between voltage, current, and resistance wasn't just some vague concept. No, he discovered that they are all tied together by a beautifully simple and elegant mathematical formula.
And this, right here, is Ohm's law. It is the absolute master key for analyzing simple circuits. It tells us that voltage is equal to the current multiplied by the resistance. V is equal to I times R. What makes this so incredibly powerful is that if you know any two of those values, you can always figure out the third one. It's like a perfect little puzzle. And just like that, we can finally solve our LED problem. We know our voltage, that's 9 volts from the battery, and we know the ideal current for a little LED is about 18 milliamps, which is 0.018 amps. So the only thing we don't know is the resistance we need. We just shuffle Ohm's law around a little bit to R equals V divided by I, plug in our numbers, and boom, 500 ohms. That is the exact resistance we need to add to the circuit to keep our little LED safe and sound.
Awesome. We've just solved our very first circuit problem. But let's be real for a second. Most circuits are way more complicated than just one battery, one resistor, and one little light. So what happens when things start to get a little more messy?
I mean, what happens when the current has options, when it can split and go down multiple different paths? Or what if you have a bunch of different loops and components all tangled together? All of a sudden, Ohm's law, while it's still 100% true, it isn't quite enough by itself to easily figure out the whole picture. For that, we need to upgrade our toolkit.
And this is exactly where the brilliant physicist Gustav Kirchhoff steps in. He gave us two more incredibly important laws that work right alongside Ohm's law, and they act like power tools that let us slice through even the most complex-looking circuits with total confidence. So, Kirchhoff gave us these two golden rules.
His first one, the voltage law, or KVL, is all about what happens when you go around in a closed loop. It's really a law about the conservation of energy. His second one, the current law, or KCL, focuses on what happens at a single point, a junction where wires meet, and this one is all about the conservation of charge. Let's see KVL in action. I want you to imagine you're taking a walk around a closed loop in a circuit. You start at one point, and as you cross the battery, you get a boost of energy, a voltage gain. Then, as you walk across components like resistors, you use up that energy, causing a voltage drop. KVL tells us something really simple. By the time you walk all the way around and get back to where you started, all those gains and drops have to perfectly cancel each other out. The total change has to be zero. And now here's KCL. This one's even more intuitive. Think of a junction, what we call a node, as just an intersection of pipes. KCL simply says that whatever amount of current flows into that intersection has to be the exact same amount that flows out. Yeah, the current might split and go down a few different pipes, but the total is always conserved. Charge can't just appear or disappear at a junction. It has to go somewhere.
So the big question is, when do you use which law? Well, this is where a little bit of strategy can save you a ton of work. If your circuit is basically a bunch of loops all connected, then analyzing it with KVL, what we call mesh analysis, is probably your best bet. But if your circuit has a ton of parallel paths and junction points, then KCL, or nodal analysis, is almost always the easier way to go. And there you have it, Ohm's law for all the basic relationships, and Kirchhoff's two powerful laws for everything else. This is it. This is the fundamental toolkit that underpins all of modern electrical engineering, from getting a single LED to light up, all the way to designing a computer motherboard. These are the principles that make it all work. So the only real question left is, what are you going to build with them?